Okay, guys, quiet. So you guys know about complex numbers, imaginary numbers. You guys learned a long time ago, not a long time ago, but last year I was two trig honors. I is root -1. A plus bi is called a complex number just because it has a real component and an imaginary component. In fact, all numbers are considered complex. The number 1 is considered complex because b is 0. You just say there's no I next to it, but that can be considered a complex number. Or just an imaginary number by itself can be considered complex. And all numbers that we can think of are complex. We have real numbers, but also so complex numbers are actually at the top of the food chain. Now, what we're going to talk about today is how to express complex numbers in trigonometric forms. You can actually use trig to describe complex numbers and vice versa. Use complex numbers to describe trig stuff. So as you guys probably did last year, you guys probably multiply and divide complex numbers. Like you have to FOIL, like you have 2 plus I times 3 minus I. You have to, or if you had like one complex number at the bottom over another one, then you had to like do the conjugate and kind of clean it up. Or maybe you had to raise the complex number to a certain power. That can be very messy if you just have the real number and the imaginary number. So for example, if you have like 2 plus I raised to the 5th power, that's a little bit messy, right? So you have to do 2 plus I FOIL 5 times, right? Or if you have like some really nasty like 2 plus I raised to the 3rd power, 1 minus I, you clean it up. That can be really messy too. The advantage of converting to the trig form is that it streamlines this process. So if you really want to design complex numbers in a more efficient manner, you want to go to trig form. And these formulas you use that enable it to combine it. So the practicality behind it, I'm going to be honest, this is incredibly trivial. It's the reason why actually I deliberately covered this the day before the final. Sorry, the last class. Not day before the final. The final's not tomorrow. Sorry, the last lesson before the final, because it's stuff that you're probably going to forget. Like doesn't get reinforced in calculus. Actually, we're going to do a lot of calculus in the second semester, so we'll do a little bit of pre-cal type stuff when we come back from Christmas break. But we're going to do a lot of calculus that we're doing. So you guys are going to get like the AP calculus A part, the first part of AP calculus AB. You get the A parts, and then next year you move on to the B part. So this doesn't really play a role, but it's good to talk about. So we're going to talk about it. Yeah. No, you guys have covered it already. No, because you guys did trig last year. You guys did cover it. Yeah. No, you're doing more than a lot that we've done like this year, like this semester, like the polar unit. That's actually going to be the BC specific stuff. Now, you guys, in terms of content or like knowledge you need to know to be successful in AB, you guys already learned it. It's actually been reinforced. So there's nothing really new in that regard. So yeah, you guys are fine. Okay, let's talk about plotting complex numbers. When you plot a complex number, the complex plane, the x-axis is considered real. The y-axis is considered imaginary. So this is the real axis. That's the imaginary axis. Or A and B. So when you see -1 plus 3i, it's not that hard. It's like saying -1 comma 3. It's the same exact thing as plotting -1 comma 3. So when you plot it on a complex plane, that's it. It's right there. -2i, that's like saying 0 comma -2. So you just plot that right there. That's it. I'll just color code to make this easy for everybody. That's like saying 4 comma -5. So guess what? 4 comma -5. And the last one, -3. That's like saying -3 comma 0. It's right there. That's all. That's how you plot a complex number. So it's kind of weird, but it just treats the same way as x and y, and the notes say so. So let's move on, because I think that's really easy. Okay, the absolute value of a complex number. The absolute value of a complex number is like distance formula. That's all it really is. So what you could do for that one, if you're asked to find the absolute value of a plus bi. Now we know absolute value in general means the distance from 0 on a number line. This is the distance from the origin on a coordinate plane. The origin is like 0 on a number line in a way, right? It's kind of analogous to it. So when you're asked to find the absolute value of a plus bi, all you're doing is doing root a squared plus b squared. So for example, if I had a complex plane, say it's 2 plus I, right? All you're doing is finding this distance. To find that distance, you just use the Pythagorean theorem, right? How long is the horizontal leg? 2. Vertical leg, 1. You need Pythagorean, what's the length of the green line? 5. There you go. That's it. That's all there is to it. So for examples 1a and 1b, 1a was negative 1 plus 3i. So the absolute value of it is root 10. Or for the other one, negative 2i. The absolute of negative 2i is just 2. It's just basically Pythagorean theorem, root a squared plus b squared. So those are kind of the basics, because we're going to be utilizing this stuff for next stuff that we're covering this topic. So any questions? No? Okay. Easy enough. All right. So when you're asked to write this in trig form, it's really very similar to the polar stuff and kind of similar to unit circle. As we know, A equals R cos theta. That's from polar, right? And B equals R sine theta. And just look at the triangle, right? Like here we got A is the horizontal leg, B is the vertical leg, R is the hypotenuse. So can tell, right? Theta is right here. If theta is right there, we use the reference angle to actually do the trick, right? Reference angle is the acute angle between the terminal side and the x-axis. And you want the closest possible angle. The x-axis, which is always acute. Sine is B over R. Cosine A over R. So it makes sense, right? Put A over R here. Take R squared to A equals A. Put B over R here. R squared to B equals B. So this means that R is going to be root A squared plus B squared, right? We know this. Tan theta is B over A. We know this. So this is all from polar stuff, right? And it's the same thing for connecting trig and complex numbers. So when you have A plus BI, it can be thought of like this. R cos theta plus R sine theta with an I to the right of it. Or you could factor out the R and write it like this. So that's how you convert the complex number to trig. So if I fill out the rest of this. So it's given by Z equals, I'm just repeating what I just wrote. So I know somewhat redundant. Where A is R cos theta. B is R sine theta. R is root A squared plus B squared. And tan theta is B over A. Just some weird terminology. I never use these terms just because we're pre-calculus owners, just talk about it. The modulus of Z, I guess, is R. I don't care. It is called argument of Z. It's like the input. I don't know if that makes sense. Honestly, I don't care. So about those terms. We'll just move on. And of course, there are implementing choices for theta because theta is coterminal, right? Like if I do 120 degrees, what's coterminal with 120? Just add 360, you get 480. So there's infinite possibilities for theta, right? So the trig form complex number is not unique, right? Because it could be a lot of different forms. I didn't have to use, like, if I have 120 for theta, I have other options for 120, right? Go around many times or backwards the other direction. So, okay, we're good? Okay, let's keep moving. So let's do some conversions. You're asked to write these in trig form. Now, you do have to be mindful of which quadrant you're in. So I'm going to do a quick drawing, but I'm pretty sure I'm going to be in the 4th quadrant, right? Kind of like this. Where clearly I'm going one this direction. Switch colors, sorry. Clearly I'm going one this direction. negative root 3 that direction. It's pretty clear, right? Yeah. So how do you do it? Well, r equals root 1 squared plus, and you put b in, not necessarily I in, even though it doesn't matter because, well, actually, no, it would matter because I squared is negative 1. So you don't put I because I squared is negative 1. You just put the b value, which is negative root 3. So you should get 2. And then tan theta is negative root 3 over 1. Now that's where you have to be in the right quadrant. What's the inverse tan of negative root 3? Just did the kind of like just punch in a calculator, or if I asked you in a class, say, what's the inverse tan of negative root 3? What would you say? And we'll do it in radians, by the way. By the way, we're gonna keep with yeah, the rest of the notes is in radians. So yeah, I know it's a pain in the ass, but let's do it anyway. We're gonna do radians. And it will be much easier for the other forms we're gonna work through in this set of notes. But yeah, what's the angle? What would it say? Negative pi over 3. Negative pi over 3, good, yeah. Because tangent 60 degrees is root 3, but if it's negative 60s or negative pi over 3. But we're not going to say negative pi over 3 because you're told to do it from 0 to 2 pi. What's coterminal with negative pi over 3 from 0 to 2 pi? Pi over 3, good. Yep. So you're going to say z equals 2 parentheses cosine 5 pi over 3 plus I sine 5 pi over 3. That 3 looks terrible. And it makes sense because cosine 5 pi over 3 is 1/2. 2 times 1/2 is 1. Sine of 5 pi over 3 is negative root 3 over 2. 2 times negative root 3 over 2 is negative root 3. That makes sense. So it all works itself out very nicely. By the way, this might help for your homework. You guys know where to locate the imaginary number in the graphing calculator? It's second decimal point. This will play a role for the more advanced stuff we do in just a little bit, because we're going to do some more advanced stuff, these problems later this afternoon. Yeah, so I is right here, second decimal point. There's I. So, for example, if I have, if I were to do 2 parentheses cosine 5, you don't have to type this down, I'm just going to do it really fast, divided by 3, plus second decimal point I sine 5 pi over 3 which is root 3, right? Because 1.73 is root 3, so 1 minus root 3i. So there you go. One thing that we'll do eventually is we're going to start working stuff like this out. Like maybe raising that to the 5th power. Does that very nicely for you, right? Or we're also going to maybe root these. Like maybe I'll take this like to the 1/5 power. You could do that for you as well. So there's a lot of cool things this can do. All right. Number 3 should be really easy. I'll just kind of give you the answer. And let's explain how 4.69 came about. You guys see how we got 5? Yeah, that's just Pythagorean theorem. That's easy, right? What quadrant are you in for part B? Yep. And unfortunately, these are not unit circle type numbers because the triangle looks like this, where it's going 4 down and 3 left. And here's your theta. So you can do tan theta equals 4/3, or theta is the inverse tan of 4/3. The problem is that's going to give you the answer in the first quadrant. Not a big deal. Add pi afterwards, exactly. If you do inverse tan of 4/3, you should get 0.927. So add it to 3.14, and that's how you get 4.06. Okay. Keep on moving. Now you're asked to do this in complex number form. So switch it, and that's not hard. 2 pi over 3 cosine's negative half. So root 8 times -1/2 plus I sine √3/2. And what's √8 simplified? Yeah, so probably a good idea to simplify it, right? Distributing should get -√2 plus √6i. Yep. And actually, it's a little lazy of me, but I should put the I to the left. Because then it looks like maybe the I is inside the radical, you know? Okay. So far everything should be pretty basic. Now let's get to the new stuff. The stuff that's kind of cool. And just for pacing, let me just see how far I need to get. We'll see if we can get there. We'll see. I can make one right now. All right. Hold on. You can't find it. Okay. Hold on a sec. We're gonna pause the video. Resume the recording. Okay, here we go, guys. So when you multiply complex numbers, you're foiling, which is not so bad if you have just two complex numbers, but if you have like multiple complex or really kind of crazy ones, it can be a bit tedious. So here's a process we can use for doing it in trig form. So before I give you the formula, let me do the formal proof of it. So if I want to multiply z1 with z2, then it's pretty clear I have to multiply r1 and r2, right? And then I have cosine of theta 1 plus I sine of theta 1 as well, foiled with cosine theta 2 plus I sine theta 2. If you foil, now I'm going to kind of save you some time. I mean, I think, well, I can do it really quickly. You have cosine theta 1 times cosine theta 2. Also, you're going to have I sine theta 1 with sine theta 2. Also, you're going to have, wait, oh, you are correct. No, hold on, back up. No, I didn't mean to write that. I meant to say I sine, I meant to say this, guys. My apologies. I meant to do that first. My bad. And then I sine theta 2 with cosine theta 1. And then I squared sine theta 1 with sine theta 2. Okay, that's supposed to be all one line. Okay, if you clean things up, you should get R1, R2. And I squared is -1, so it becomes cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus I on the outside, sine theta 1, cosine theta 2, plus sine theta 2, cosine theta 1. You guys follow me? I squared, -1. We're okay? Okay, let me back it. Let me just pause a sec. So the foiling is a little messy, right? Cosine theta 1, cosine theta 2. I sine theta 1, I sine theta 2. We're okay with that. Then the middle, the outside, and inside, you got sine, I sine theta 1 with cosine theta 2, I sine theta 2, cosine theta 1. And then you combine stuff that don't have eyes. Combine stuff that have eyes. If you use a sum and difference formula, remember that. That would be nice. That'll be cosine of theta 1 minus theta 2. No, I lied. Plus. Plus I sine theta 1 plus theta 2. And then all that multiplied by R. Yep. So why I just let me highlight it so it stands out.
And you did that with
some difference formulas.
It's kind of hard to read.
Sorry. I'll write again. Guys.
That made it clear.
Thanks. So it's just the formal proof of it, right?
So you don't have to do it the initial way, right?
No. I'm just showing you where this formula comes from.
Okay.
Once you know the formula, you see the point.
Okay.
No, I'm not saying you guys do this. I just want you guys are honest students. I know you guys can handle the proof, so I'll figure out the proof. Okay, go ahead.
What about the weird binomials we don't really have? Like the can't you do like the power and then you like
We're getting there, actually. That's part of this. We're getting there. Oh, yeah, Pascal's triangle. Yeah, or binomial theorem. So
No, probably.
and guys, quiet please. By the same token, I'm not gonna do the form proof for division in the interest of time, but by the same token, you could do the same thing. You could do some sort of combination of these trig functions, but essentially here's what you got. It's R1, R2 times bracket cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So it's not hard where it comes from if you actually go through the foiling process, but ultimately you'll just use that formula. And if you're dividing, it's going to be R1 over R2, and it's just the opposite. Cosine, this gives me theta 1 minus theta 2. And just trust me, if you go through the process, it will work out this way. If you want to test that yourself, go for it. But I'm not going to do it in the interest of time. Which part are you?
How did we get from R1, R2, cosine theta 1, cosine theta 2, and all that stuff to
That was using the difference formulas from trig. Because when you have like a sine, we have sine of an angle, we have sine A, sine B minus cosine A, cosine A, cosine B minus sine A, sine B. That's cosine of A plus B.
okay.
Yeah.
Okay.
Yeah. Or if you have like sine A, sine B plus cosine A, cosine B, that's sine of A plus B. Yeah. All right, so if you wanted to FOIL this and work these out, you can. But now I just know I'm going to multiply these two R's together, right? I'm going to add the angles and take their trig values. That's it. So now I know what to do. Bless you. 2 times 8 times cosine of 2 pi over 3 plus 11 pi over 6
Yeah, it would be exactly that.
so 16 times a little bit of math you have to do here. That's 4 pi over 6. So you should get 15 pi over 6. Right? 15 pi over 6, which is 5 pi over 3, by the way. No. 5 pi over 2. Is that right? Yeah, because each of these are going to be 5 pi over 2. 5 pi over 2 is 1 revolution around, stopping at pi over 2, 90 degrees. Cosine there is 0. Sine there is 1. So the answer is a 16i. So that's what you can use. That's the advantage of the trig form. It just kind of streamlines the process a little bit, right? Like let's just combine these angles. Yeah. Yeah. Well, I just reduced it, and it becomes pi over 2 after that. Same thing. I didn't want to skip any steps, so. But yeah, you can think it's pi over 2, sure. Okay. Why don't you guys try example 6 on your own really quickly? Now, in this case, there are degrees. I said we're going to use radians, but there are degrees here. Try example 6. I'll give you guys a couple minutes. Then we'll move on to powers and zeros of complex numbers.
Probably can.
What? You do 300 by 7. Like 325. Yeah. 325.
That's just 15, right?
Yes, 20.
Pretty good.
Wait,
Oh, sorry, what was that, Brooke?
Oh. Are we trying
225 plus 225 is equal to negative 2. Stay happy. 24 over 8. George, you guys get 24.
So what's our
You're not great.
Okay, you guys should get this, hopefully.
Yeah, that's fine.
Yep.
Oh, you don't multiply that.
You get 3 over
4. Okay. Same thing. That works too.
Oh, that's so right.
Yep. You're okay? All good? All right, let's keep moving. All right, now let's talk about powers. Okay, so Kate, you were asking about this, right? So we have, yes, there's something called the binomial theorem, which you could use Pascal's triangle, blah, blah, blah. We don't need that for this. There's a much easier way because these are complex numbers. We can combine things a little more efficiently. First off, let's see what happens when you get z squared. If you want to do z squared, obviously you're doing this. R cosine theta plus I sine theta times R parentheses, you just got to repeat it, right? And of course, you got to multiply it out. Which actually becomes this, if you were to multiply it out, just kind of trust me on this one. It does work out this way. He uses a double angle.
Yeah, no, that makes sense.
Just 2 sides.
Oh, yeah, no, he's right. He's right.
I know I'm right.
He's called back. He's right. He's right. That's no proof.
And then you got
Yes,
this.
he's right. Just think about it. Think about it. -1.
Cosine squared minus sine squared, cosine. And here you can talk about I. What sine theta is, that's sine 2.
Oh.
What's the 2 times cos theta?
One just like use the addition.
That's you. That's where the one point comes from. So that's what happens when you square z, right? You square that. You get this. Now I'm not going to do all these in their fine glory because it just takes way too long. So I'm just going to just show you what happens.
If you do, well, actually, what happens? No, here's what happens. You wind up getting z cubed. Z squared is this, right? Sorry, z cubed is this. You would agree, right? And z squared we just did. Z squared is, r squared cos 2 theta plus I sine 2 theta. And then times r cos theta plus I sine theta. Now, if you were to FOIL this, it gets really nasty. I'm not going to go through the process, but if you were and use some difference formulas, you wind up getting this. R cubed cosine 3 theta
That makes sense.
Oh, yeah, he's right. Guys, he's right.
Yeah, I'm right again, I know.
Okay.
Okay, so anyway,
If you were to actually go through the motion, guess what? Cos 2 theta times cos theta, and then you have I sine 2 theta, I sine theta becomes I squared theta 1. It actually represents the sum difference formulas for cosine. That'll be cosine 3 theta. And then if you combine the outers and inners, I sine 2 theta with cosine theta, I sine theta, cosine 2 theta. Combine all that, that's actually going to be the sum difference formula for sine.
which becomes sine 3 theta. So we have a conjecture here. Ultimately, I could just say this now. R4 cos 4 theta plus I sine 4 theta. Or R5 cos 5 theta So what happens, it becomes this, guys, R to the N cosine and theta plus I sine and theta and that. That's all. And it's called Demois's theorem. It's one of the things that I don't think they cover in the AV class anymore. When I taught AV, I used to teach pre-Cal AV honors. So yeah, that's all it is. So if you see the whole complex on raised to the n power, again, it's just this. It's not distributive necessarily, guys. So don't think of being distributive because it's not really distributive. It's just that if you actually were to FOIL this over and over again, it works out this way. There we go. Okay, so questions? All right. So example 7, we're going to apply Demois's theorem, which just means you identify what R is, you identify what theta is, and you just go to trig form and do it. So here we go. So R is going to be what? The R should be pretty easy. What's R, guys? 2. Theta should be pretty easy. We're in the first quadrant. What's theta going to be? Five or 3? Yeah.
Wait, mystery.
Yeah.
Can I clarify how we got?
A squared plus B squared.
Square root. You raise 1, you beat root 3. 1 plus 3, root it, 2.
Okay, so here's what we're gonna do. I'm gonna do so 1 plus I root 3 is 2 parentheses cosine pi over 3 plus I sine. So now if I want to raise it to the let me erase this other stuff here. We do this, guys.
Oh, it's 8 negative
Oh, that was my mistake.
Cosine.
I swear just equals 8. Negative. I you can't do
Oh, that's negative.
I got that.
It's the same exact thing. If you did 1 plus I root 3 FOIL 3 times, you get the exact same thing. But this is just a more streamlined process. Whereas, hey, R2, my theta is 5 3.
Oh, yeah.
Split it to a form. Let's use Demois's theorem, which is the formula that I apply. That makes the third power, multiply the angles by 3. Use your circle. You're good.
By the way, I used to teach this like over like at least 3 or 4 different like class periods for a few. So I'm doing it kind of quickly with you guys. But I think you guys can handle it. Okay, why don't you guys try example 8? Try example 8, see how it goes. Should take about 2 or 3 minutes.
What are we doing?
I'll freeze my screen.
So R is equal to 1.
Yeah, R's 1, guys. Theta is 3 pi over 4.
So, 1 to the power of. Wait, Mr. Eden, couldn't theta be 90 plus 45 and also 180 plus 45? Like, couldn't they be
No, we're in the second quadrant. We're not in the third quadrant.
Don't worry. Also, it would
Your A is negative, B is positive. You have to be in the right quadrant.
so yeah.
Yeah, you gotta be in the right quadrant.
Right here.
That's root 2 over 2. 15 power equals 8. 9, 10, 11, 12.
7 power versus 7.
Is that it?
Here.
Yes.
Well, should give you-
Let's get this. 2 over 2.
You guys have root 2 over 2
Divided 5 or 2.
plus
That's it. That's it.
minus.
Divided 5 or 2.
Oh, wait, no,
Okay, so I get guys.
Raise 1 and theta is 135 split. That's all I have.
Okay,
What do you need to use?
questions? Questions at all? Pretty straightforward. We're okay. Okay. So, I'll take some questions before we do the last part. Yeah.
No, we're in the fourth quadrant.
Ever happened?
You're almost done 2 full resolutions.
Let's
Let's go through all 7 times.
What makes them use the Moivre's theorem? The Moivre.
You're Q4.
Mr.
X is positive, Y is negative. That's Q4.
Mystery.
Right?
Why? After pre-calc, when did you use the Moivre's theorem?
Never. Never. No, when I taught pre-calculus as a teacher, that's it. Yeah, you don't use in college. Like you don't. The calculus you will use a lot in college. These different colleges, yeah, but not this stuff. This is very trivial. It's just kind of a neat math thing to do. That's really what it is.
What are the polar functions? Does that give up a lot of calculus?
And AP Calculus BC it is. Yeah. All right, guys. Guys, quiet, please. We got a few more minutes. I want to squeeze this in as quickly as we can. Now, guys. Thank you. All right. So, x to the 6 minus 1 equals 0. When you see this, now don't do this. Some people might think to themselves, there's just 2 answers. Some people think, and don't write this down because it's not correct. They'll just take the 6th root of both sides, right? And because it's even roots, they'll do plus or minus, which is good. You should always put plus or minus with even root, which is true. However, because it's a degree 6, you guys learned this in algebra 2. The number of solutions you have, whether it's real or not real, actually the number of complex solutions you have should always be equal to the degree. If I were to graph this, I'll only see 2 answers, right? If I graph x6 and y equals 1, or graph x6 minus 1, I'd only find 2 x-intercepts, right? 1 and -1. There are actually 4 invisible x-intercepts that are complex, okay? And so if I were to go through the motions, now in this case, here's how you really would have to do it. That's actually a difference of 2 squares, believe it or not, right?
Oh,
And then that's the difference of cubes. You guys remember this?
Yeah, I do.
You guys remember this?
Yes.
So I do
We never, she told us we needed it for a test.
use it
And
like
then
one
we
time.
just, it just wasn't on the test, but we like memorized it.
And guess what?
These two here, if you did swap form for each of these, will provide imaginary solutions. Right? You did swap form for each of those.
I think this one is,
Ario did not go out.
if I'm not mistaken, -1/2. Okay, so
Next slide, please. So this gives us 6 solutions now, because if I did the difference of squares, then difference of cubes and sum of cubes, then you got these quadratics, and you plot form for each of those, these for every line, you get the complex solutions.
that's not terribly efficient to keep doing it this way. So there is actually a more efficient way to find the roots of complex, because essentially what you're doing, you're finding the 6 roots of 1. And 1 is a complex number. It just doesn't have imaginary number connected to it, but you could think as a complex number if you want. How do you find the roots of complex numbers? You use this formula here.
Oh.
Okay.
So if something's raised to zero power, so u equals a plus bi, it says raised to zero power, so it's a plus bi raised to n power. If you want to take the root of this is not, it's a little confusing. And I got to bring this on the trash for this week then. It's a little confusing. But here's what you do. You do all these iterations. You start with k equals 0. And you work it out. So first you got to figure out r theta. So you have a complex number, figure out r theta r. And you assume k is 0, and you work it out. You assume k is 1, work it out. K is 2, works out. K equals 3. Until you get n minus 1. So if I have 6 root, I got to do 6 times. K equals 0, K equals 1, K equals 2, K equals 3, K equals 4, K equals 5.
Oh, that's really
When they get really complex, no pun intended. You like that? Ah, ha, 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 right? Yeah. Okay. I'm not gonna. I'll save this for you guys. You guys have to fill out notes. I'll save it for you guys on Friday. I'll do it again with you guys. But if I show you the filled out notes for example 10, here's how it looks, guys.